Welcome to the Magma and the LMFDB mini course. I'm going to do this mini course by relating Magma and the LMFDB to things you see in the other mini courses this week. So this talk will be about lattices and quadratic forms, which relates directly back to Keith's talk right before mine and to his whole mini course about lattices and quadratic forms. I'm not going to replace their mini courses, naturally. I'm just going to present some computational aspects and touch upon the same things from a computational angle through Magma and the LMFDB and show you what you can do and how you can do research related to these things using these tools. So today, the talk will be structured first by introducing Magma and showing you a little bit of how to work with it. You all have gotten through Zulip some messages about access to Magma. And I'll relate to it more today. But everything we do in classes will be very, very easy and things that you can do online. You don't need to have any Magma installed on your computer for that. If you want to do some more heavy lifting, something in the project or the problem sessions, then you might want to have it installed on your computer. After introducing Magma, we will talk a little bit about quadratic forms, review some of the things you just heard from Keith, and we'll proceed to lattices and theta functions. And in the last part of the talk, I'll show you a part of the LMFDB that's related to lattices and quadratic forms. So what is Magma? So Magma is a computer algebra system. There are several of those. Some of you may be familiar with others, like Sage or PariGP. And Magma is specialized in algebra, number theory, algebraic geometry, and algebraic combinatorics. It's being developed at the University of Sydney. And it's powerful for things like number theory and algebraic number theory, lattices, modular forms, curves and abelian varieties, group theory. And if you just want to run a few sample calculations, there's an online version. The Magma calculator that you can click on. The slides are also available in the GitHub repo that Alvaro shared with you. And I think you all also have access through Diophantus to Magma. So that was messaged earlier today. OK, some basic syntax in Magma. So words are case sensitive, and statements have to end with a semicolon. If you want to assign a value to an integer, you don't just write equal, you write colon equal. And it will take me a second to show you what I'm doing. All right, so I can assign a value to a variable. I can work with lists or sequences. Now, sequences in Magma start with 1. This might annoy some of you who are used to programming, and it takes some getting used to. But it is, mathematically, it does make sense. OK. Now I have to get back. Yes. So there are several basic types in Magma. Magma is strongly typed. So, for example, you can't often do operations between different types, and you really need to know what your types are when you're using some function. There are integers, rationals, real numbers, complex numbers, the ones you would expect. There are also sequences, like we just saw. the elements in a sequence must belong to the same universe. So when we had a sequence of integers, that was easy. But if you want elements from different universes, you need to use lists. You can manipulate strings easily. And of course, there are many other rings or fields that you can construct. If you want to further explore and understand what's out there, there's an online handbook that you can view. Or you can just type the function name in the terminal. There is also the useful function of list signatures. Maybe I'll briefly go back. So for example, if I'm looking at the type of n, I can see that it's a ring int elt. So it's an element of the ring of integers. I can also look at its parent, which is the integer ring. Now, what might I want to do with this integer? I don't know. Maybe I care about the prime 4003, and I want to know for this element in modulo 4003, I want to know what its discrete log with respect to like what power of 2 do I need to raise to get to this one. So I can do something like this. But of course, how would I know that this function even exists? Well, I could search for, okay, I guess I cheated a little. This element is no longer an integer, right? It's an element of a finite field. But I can look what I can do with a finite field element. There are many such functions. But maybe I only care about the log function. And it will tell me what I need to type in order to get the log of a finite field element. I could also just type log and see what kind of log functions there are. But as you see, there are many log functions involving different things. For example, there's a log of binary quadratic forms, which is an interesting thing by itself. But let me not dwell too much on this. And go on to quadratic forms. So, yes?
So I saw on the terminal you did this thing with like the exclamation mark. Is that like a typecasting thing?
Yes, this is a coercion. So you can often coerce from one structure to another. In this case, we wanted to coerce an integer to a finite field element because there's a unique natural way to do so. All right. So we've seen that quadratic form is a quadratic polynomial in many variables. There's also a basis-free version that I present here that basically tells you that when you multiply by a scalar, this scalar acts quadratically, and that this associated bilinear form that we saw earlier is bilinear. Notice that here BQ is twice the bilinear form we saw earlier. I could have changed that, but I think it's important because these notions and definitions vary a lot for different reasons. And it's something worth pointing out and noticing which definition you're looking at. And we'll see this also on the LMFDB in the end of this talk. So there are several things that are related to such a quadratic form, some key invariants. So there's the Gram matrix, which is the matrix representing this form with respect to a basis, the same matrix M we've seen earlier. There's the notion of an isometry, which is the same as the change of variables, the integral change of variables we've seen earlier. So an isomorphism between two quadratic spaces that preserves the values of the quadratic form, so sends elements of certain length to elements of the same length, is an isometry, preserves distances. And we have the notion of a discriminant, which is basically just the determinant of this Gram matrix. Notice that the determinant of the Gram matrix is not a well-defined invariant of the quadratic form, but every time we change basis, we multiply this determinant by a square. So up to squares, it is a well-defined invariant. So what this quotient here means, it's a representative element in the field up to squares, or non-zero squares. Here's an example. You take some nice quadratic form, binary one, x squared plus xy plus y squared. And if you write the gram matrix with respect to the standard basis, then you get 2, 1, 1, 2. Notice again, this is with the bilinear form that I wrote now. With the bilinear form from Kittstock, you will get 1, half, half, 1, just a scaling by 2. And the discriminant of this form will just be the determinant of this matrix, which is 3 up to squares. All right. Okay. Now, how do we work with quadratic forms in Magma? This is, again, very straightforward. So I want to define some quadratic form, so I'll need to define a polynomial. So I can define a polynomial ring, saying the variables x and y, and say it will be over the rationals with 2 variables. So now R is just this polynomial ring of rank 2 with variables x and y, and one can form the quadratic form x squared plus xy plus y squared. How do I use it as a quadratic form? Well, I can construct a quadratic space from this form. So this is a vector space, 2-dimensional one, with this inner product matrix. You see the same inner product matrix that I presented earlier. You can get it by writing gram matrix of this vector space. And I don't know, what else would I want to do with a quadratic vector space? Well, maybe I want the determinant of this gram matrix. Again, 3 as we've seen before. Oh, whoops. All right. We're now coming to the step of wanting to do more with these quadratic forms and the notion of certain forms being equivalent. So of course there are many, many forms, but some of them are just the same forms in disguise because we can make an integral change of variables and get from one to the other, or an isometry to get from one to the other, as the example that you see here. Sometimes it's also easy to see that some forms are not equivalent. For example, this first example here with x squared plus y squared plus z squared, and not isometric to x squared minus y squared minus z squared, you can see it by just looking at the eigenvalues, right? On one side, they're all positive, or maybe better, the x squared plus y squared plus z squared is positive definite, and you don't have any any vectors with negative length. On the other hand, for x squared minus y squared minus z squared, you do have. So this is something you can capture by positivity or negativity. So you can capture that over the real field. You don't need to know any properties of the rationals of these forms, any integral properties, for example. For the other form, like the x squared plus 5y squared and the 2x squared minus 2xy plus 3y squared, they're both positive definite, so that wouldn't work, but they're still inequivalent. And that might be not trivial to see at first, but if you look at the x squared plus 5y squared, you'll notice easily that if you plug in integers, you only get things that are squares modulo 5, right, because of the 5. On the other hand, for the other form, if you just substitute something like 1, 0, you get 2, which is not a square modulo 5. So you see that they don't represent the same numbers modulo 5. And this property of not being equivalent at 5 with respect to the prime 5 is something that one can characterize as these forms being inequivalent over a certain p-adic field, the 5-adic field. Now, this inequivalence is also related to class groups of number fields, and we will touch upon it tomorrow. Now, the nice thing about quadratic forms is a very deep theorem of Hassan-Minkowski that's two quadratic forms over Q are equivalent if and only if they are equivalent at every prime and over R. So if their signatures are the same and locally at every prime they're the same, then there's actually an isometry over Q, a change of variables over Q that relates one to the other. This is the deep theorem, and I'm not going to say anything about its proof. But I do want to say that it tells us that in order to classify equivalence classes of forms over Q, all we need to do is to be able to classify them over every prime. And a way to do it is by understanding over prime P what are the key invariants that can allow you to completely classify a quadratic form. So naturally, you'd need the rank and the determinant, but that's not enough. There's an additional invariant that we call the Hassan-Minkowski invariant, which is either plus or minus 1. So it's just one sign that tells you which class this form belongs to. All right. Now the right thing to do is to see how we can actually compute this thing, right? How we can check this thing in Magma. So say we have these two forms, x squared plus 5y squared. And we have the form 2 times x squared minus 2xy plus 3y squared. Right? And we can create the quadratic spaces corresponding to these two forms. And we can ask, are these isometric? Whoa. And there's an error. Okay, I know this error is because I'm using an old version of Magma right now. This already exists in the newest version of Magma. But of course, if you hit an error or see something that shouldn't be there, you can always report a bug. So Magma is a public bug tracker. You can submit a bug here, and you'll get a response. Either way, for us just now, maybe for just to see that it works, we can change the ring here to some finite field, say GF5. Oh, I forgot the semicolon. Okay. And now first argument is even degenerate. Okay? So they're clearly not isometric. They're so clearly not isometric that Magma is even telling me there's no use of trying to check if they're isometric. You could also directly check the Hassan-Minkowski invariant. Wait. Right, showing you that they have different Hassan-Minkowski invariant at 5. And again, you see that sometimes I try a command and it doesn't work because I'm using the wrong types. For For example, this command didn't accept the quadratic space as a parameter, only the actual quadratic form. Okay. All right. All right, so Hassan-Minkowski classifies forms over Q by looking at them locally at every prime. But what if we change this picture from Q to Z? So instead of looking at vector spaces, we're looking at some lattices inside these vector spaces. So really a billion groups or Z modules. So for lattices, this local to global principle that the Hassan-Minkowski theorem gives us no longer holds. So this principle fails. So before I show you how it fails, I'll say a little bit more about what are these things. So for us, we will work over a ring that's a principal ideal domain. So every ideal is generated by a single element. You can think in your mind just about Z, the integers, though it will be useful for us also to look at the p-adic integers. And its field of fractions will be F. So you can think of F as Q. And we have some quadratic space over this field. So a lattice, or an R lattice, is a finitely generated module that contains a basis. So this definition of having to contain a basis is not standard. Sometimes people call it a full lattice. But in this talk, I'll only talk about full lattices. So these are lattices that actually span the entire vector space. And the point is that these lattices are just free modules over this ring R. And maybe the right way to think about lattices is how you have them in your mind, something that looks like this, right? This is a lattice in 2 dimensions, right? Spanned by these 2 vectors, and you can extend it to higher dimension by having more vectors. Now, we will be especially considered, because we're doing arithmetic and number theory, we'll be considering things that are integral. So what do we mean by integral? We want the bilinear form on the lattice to attain integral values. All right? So this is like, okay, one could say that this is just a scaling issue. So for every lattice, you could scale the quadratic form by something to have it be integral. So for example, a lattice whose Gram matrix has integral entries is integral. And we will say that the lattice is even if the quadratic form that it represents is integral over all the elements of the lattice. So if we take a basis for this lattice and we find the Gram matrix with respect to this basis, it will mean that we will have even entries along the diagonal. That's why it is called even. So remember that we have bxx in our notation is just twice qx. So the bilinear form, if the quadratic form is integral, then the bilinear form is even. Okay. So now, if we have an integral lattice, the Gram matrix will have entries in our ring, right? It will be integral. And because every time we change a basis, the change of basis matrix will have an invertible determinant. This determinant is now determined up to squares in the multiplicative group of the ring, right? Things that are invertible in the ring. If you think of the ring as Z, then things that are invertible in the ring are just 1, -1, right? And squares of these are just 1. right? So over Z, we just get an element of Z, which is very convenient. All right. One small note. Tomorrow, we will also meet lattices over other rings that are not principal ideal domains, rings such as the rings of integers of number fields. And there is also a notion of a lattice there. It is just no longer free. So it doesn't have to be of this form of like direct sum of copies of the ring. It could have some other form, something that is known as projective. That means that locally it is free. But that's for later. I talked enough. Let's see some examples of lattices. So again, our most important examples will be when R is just Z, the integers. And for now, we'll just take the quadratic form to be the standard inner product. And maybe a very famous root lattice is just the lattice Dn, where you take all the vectors such that the sum of the entries is even. It is a nice exercise to see that this lattice has discriminant 4. And it's quite easy to see that it's even almost by definition, right? We just defined all the vectors whose quadratic form is even. Okay. One can also construct a lattice from this Dn by adding one vector, just the vector with all entries a half. And we usually call this lattice En. Notice that it's integral if and only if n is divisible by 4, because of all these half squared to a quarter. And it will be even if and only if n is divisible by 8. Okay? So when n is divisible by 8, this lattice is both integral and even. And again, it's not too difficult to see that its discriminant is 1. Maybe the smallest example is a famous lattice called the E8 lattice. So, yes?
So are we considering discriminants modulo squares?
So, as I said before, for lattice, where we're looking at things up to integral equivalence, the squares are squares of invertible elements in the ring. And when the ring is the integers, this is just 1. So yes and no. So this particular lattice, E8, gives the densest sphere packing in dimension 8. This is a result of Wiezowska from 2016, won her the Fields Medal in 2022. In dimension 24, this role is played by the well-known Leech lattice, one of the 24 Niemeyer lattices, and the symmetry group of the monster group, which is like the largest finite simple group. And if you have the slides open, you can feel free to click the link and explore a little bit these lattices. Okay. How do you work with lattices in Magma? Well, again, this is quite straightforward. One can just define a lattice from a basis or from a Gram matrix. So maybe I'll start with a basis. So I can take these 3 vectors, 1, -1, 0, 0, 1, -1, and 0, 1, 1. So you can see that this is a basis for D3, for example, right? All the vectors whose sum of sum of entries is even. And I'm getting here a lattice. I can check what is the determinant of this lattice, and I get 4, same as we've seen earlier. I could also construct a lattice from its name. So I could construct E8. Just construct a lattice. This is the basis. and I can ask what's the determinant of this lattice, get 1. So that is really a unimodular lattice. And I can ask if a lattice is even, and if it's integral, maybe. Yes, I think so. Okay. Oh, and I can ask about the shortest vectors in a lattice. One thing that one needs to notice here is that E8 has 240 shortest vectors, but Magma will only tell you that there are 120. The reason for this is because shortest vectors only returns one of each pair of a vector and its minus. So there's a natural symmetry, right? A vector and minus the vector have the same length. And this is just, again, a matter of notational definition. All right. So now we can talk about equivalence of lattices, right, or isometry of lattices. So we say the two lattices are isometric if there's an isometry between the vector spaces, between the quadratic vector spaces that map one lattice to the other. So we know, same as we did for from vector spaces, that if there's an isometry between two lattices over Z, then they're also isometric over ZP, like the p-adic integers for every P, and they're also isometric over Q or over R, right? But unlike over Q, the converse fails. And because this converse fails, we try to measure the failure. And for that reason, the same Gauss that you met earlier today in Alvaro's talk, in his Disquisitiones Arithmetica, introduces the notion of a genus. And lattices with the same local data, meaning that they're isometric at every prime P and at R, are said to lie in the same genus. And now one can ask, how many isometry classes are there in the genus? And this is what is known as the class set of the lattice. Okay, so here is an example. This is the famous example actually found by Witt and later used by Milnor in 1964 that Kit talked about. So if you look at the lattice we saw earlier as E16, like En with n equals 16, then its class set consists of two isometry classes. There's E16, and there's the direct sum of E8 with itself. So these two lattices are not isometric. They're both determinant 1, even, and have rank 16. Here's another example, a smaller rank example. So here we have two lattices. You can see pretty quickly that their determinant is 22. And it's less quick to see that they actually lie in the same genus. It's possible to see this, and we'll see this in a few slides. And the class set in this case just consists of these two lattices. So again, they're non-isometric, but in the same genus, as we'll soon see. Okay, and the question I'm going to ask you now is how we detect these isometries and how do we enumerate these class sets computationally. So here's an example of how we test isometry of lattices in Magma. All right, so now we have some gram matrix. So this is a symmetric matrix, so I can type it in a little faster. So this just gives me the symmetric matrix that we just saw of determinant 22. And I can construct a lattice with this gram matrix. So just lattice with gram of G. And we get such a lattice. And we can also construct the other gram matrix. And construct a lattice with this gram matrix. And we can also ask what is the quadratic form related to each of these gram matrix, to each of these lattices. Sorry, this was L. Okay, notice the factor of 2 here. Again, this is because of the definition, different definition of a bilinear form. So if you want to get rid of it, you need to divide by 2. But you'll see that this is the first quadratic form we saw earlier. And one can do the same with the other lattice. And we can check if these 2 lattices are isometric. Isometric. And get the answer false, right? That they're not isometric. All right, so how do we enumerate the class group? We use the class set. We use an idea that goes back to Kneser called p-neighbors. So if we have 2 lattices, we say that they're p-neighbors if their intersection has index p in each one of them. Basically, you have lambda here, lambda 1, lambda 2, and their intersection, and you want this index to be p for each one of them. The nice thing about p-neighbors is, first of all, is that they belong to the same genus, and more importantly, if you choose your primes correctly, then by traversing p-neighbors, you can reach every lattice in the genus. This is the nice thing about them, and this is actually the way that Magma produces the genus of the lattice. So you just go on this p-neighbor graph and find all the isometry classes. As a bonus, one also gets some interesting operators, Hecke operators on these isometry classes. But we'll talk about this more in the last lecture. Yeah. So again, you can use Magma to just enumerate the genus representatives. Right? If we have this lattice L, you can ask about its genus. It will give you some symbol, but you can also ask for the representatives of this genus. Here you see that there are 2 genus representatives, exactly these 2 representatives we've seen earlier. And you could also ask what are the neighbors of one lattice with respect to some prime, say the 2 neighbors of this lattice. You get list of its neighbors. Okay. This is actually the way that Magma computes the genus, by enumerating the p-neighbors for appropriate p's. Okay. Now, suppose you're interested in lattices and their equivalence classes up to isometry. You want to measure these class sets. You're interested in how they behave. You might want to know a little bit more about them. You want to have some database of them so that you'll be able to explore this further. So there are many attempts of having databases of lattices, and there are many incomplete ones. And at the moment, we're working in the LMFDB on having better linkable version of a database of lattices. Before one does such a thing, we need to think, well, how many lattices do we expect to find? And maybe more importantly, how many genera of lattices do we expect to find? So given a rank and discriminant, how many different genera will we find there? So one can try to count these things. In recent work with a few high school students, we show that this is basically polynomial in the discriminant with a small power and linear in the rank. And we have some version in the alpha version of the LMFDB that you can go ahead and browse and look at. It's searchable by many things like rank, class number, theta series. There's also a lot of work on low rank and low dimension enumerating of genera. There's a recent paper of Chenevier and Taibbi where they enumerate all the unimodular lattices of rank 29. That's like the state of the art. And the enumeration mostly uses Kneser's p-neighbors method that you see. Like many improvements built on it, but this is like the basic building block. All right, just a quick reminder of theta functions. You just saw it in Keith's talk, so I won't say much. We have representation numbers. Before they were represented as representation numbers of the quadratic form, but you can also think of them as representation numbers of the lattice. So like these are the number of elements in the lattice that the quadratic form gives this value on them. Like if you take the lattice to just be the standard lattice, z to the n, then this is the same as the previous definition with the quadratic form. And you've seen this example of the sum of two squares and the first few representation numbers of this lattice. And of course, we package it into a generating series, giving us a theta function associated to this lattice. So clearly, if we have two isometric lattices, their theta functions are the same because the representation numbers are the same. And the converse, as Keith said, is false. And this is the example that Witt produced in 1941. So we're going to look at the theta series of these two lattices, E16 and E8 plus E8, and see that it's the same, even though the lattices are not isometric. And we can do this all in Magma. So again, we can just construct the lattice E8 from its name in Magma. And we can construct the theta series. I'll give the variable the name Q. Theta. I need to be able to spell theta. And say I'll show it up to precision of Q to the 9. So theta E8 is this power series, and I need to specify where I want to cut off the Q expansion. I could also create the direct sum of lattices, say the direct sum of E8 and E8. Okay, so these are the two copies of E8, and construct the theta series of this lattice. Oh, what did I just do? Oh, I forgot to tell it to what precision. Okay, so you get this thing, and it looks very similar to what you would expect. So when you take the direct sum of lattices, it's not too difficult to show that the theta series you get is just the product of the theta series of the two lattices. So in some sense, this theta map is a homomorphism. So this is the series of E8 plus E8. But the more interesting thing to do is to construct a theta series of E16. Now, Magma can't produce E16 in the same way because it's not what's called a root lattice. But we can construct it the way I told you. So you take D16 and you add to it this one vector. So this is, I can just construct it as a lattice of rank 1 that all its coordinates are 1/2. And you can see some other symbols that I'm putting in. So we have a predicate here, half such that I is in 1 to 16. So this is just 16 times 1/2. So E16 is this lattice. And you can check that theta series of E16 again, I need to specify precision, is the same as the theta series of E8 plus E8. Okay. If you say this might be a coincidence, they might only be equal in the first 9 terms, then you can do something like theta series of E16 20 minus theta series E8 to 20. Oh, maybe 20 was too far. That might be a long computation. Okay. Things to remember. This computation is not at all easy. It might seem like a trivial thing because I type something and get the immediate result, but this actually involves counting short vectors in 16-dimensional lattices using some very complicated algorithms. But maybe the thing I wanted to show you is that these are not isometric. So I'll have to start again. But this wouldn't be too difficult. I just need to create D16 and E16 the same way. E8-2 is the direct sum of E8 with itself. And then I can ask, are these isometric? And the answer is false. And this is one way to see that the theta function does not determine the lattice, as we now know, or one cannot hear. All right. So this was a nice demonstration of Magma capabilities and how we can construct lattices, construct theta series, show that one cannot hear the shape of the drum using Magma. But I also want to tell you a little bit about the LMFDB. So the LMFDB is a searchable database of mathematical objects from number theory and arithmetic geometry that has extensive cross-references between the different fields and domains. What's in it? Pretty a lot. So there's number fields, there's elliptic curves, there's L functions, there are modular forms, there's groups, there's Galois groups, and many other things that you can explore. What interests us today are the integral lattices, and there are 2 versions. So there's a beta version of the LMFDB, which is soon will be obsolete, and there's an alpha version that we're currently working on. So if you click on this link and mirror it, then you'll get to this page of integral lattices in the alpha version of the LMFDB. You can see that it's written here alpha, so this is the right place. So there are pages for lattices and for genera that you can pass between. So you can see that there's quite a lot of lattices here, with class numbers reaching up to 917, which is quite a lot of enumeration, with rank up to 26. And you can do things like search for your favorite rank 3, discriminant 11, even lattice. And you'll see that there are 2 of them. These matrices might seem familiar from before. And if you click on one of them, you'll see a lot of invariants for this lattice, like the level, the class number, the genus symbol, the automorphism group, all kinds of other things that you probably don't know, but if you click here, you'll see some explanation. And if this explanation doesn't satisfy you, you can click further and learn some more. There's the theta series. There's an Euclidean basis. So remember that Kit said that you can look at every positive definite lattice as something inside Euclidean space, inside over R. So this is a way to embed this lattice over R with the standard inner product. There's the quadratic form, and there are other things that people care about. There are p-neighbors that we just talked about, Kneser's p-neighbors. You can see what are the p-neighbors at 2, at 3, and at 5. In this case, we only have 2 isometry classes in the class set, so that's not very interesting, but you can go to the genus. Oh, that's not good. Okay, as you can see, this is still an alpha version, and not everything works. But if we go here and search the same thing, I was certain this worked when I tried it, but okay. We can find the genus. Okay. I don't know why it doesn't work now. In principle, you could find the genus. Maybe I'll look for a random genus and hope that not everything broke. Let's try this one. Okay, maybe everything broke down. Wait, why is it lattice genus and not just genus? Okay, it's okay. Okay, so this spoils some of what I wanted to say, and that basically one of the projects that some of you will be able to do this week is to improve exactly what you saw now, so that these things wouldn't break, and you'll be able to see the genus. Okay, what just happened? I see. All right. Now, why do we want to use the LMFDB to search lattices, right? We can compute everything in Magma, say. So the nice thing is, as you saw, there are some computations that are expensive, right? Trying to compute the theta series with large precision. You don't want to repeat them over and over again. You just want to do them once and then look them up. So you can do quick lookups without rerunning these expensive computations. It's also cross-checked and verified. So you know you didn't do a silly mistake. And there are cross-links. It connects to the associated genus, to the modular form, etc. These are exactly slides that I prepared in case something breaks. So we found this lattice, but we couldn't get to the genus. It's okay. So if you go to the web page, for example, for E8, you could go from there to the Eisenstein series E4, to the weight 4, which is a weight 4 modular form in SL2Z, and the LMFDB page for E8 will link to the page for E4. From there, you can go to the Dirichlet character, which links to the zeta function, which is its corresponding L function. Okay, so I'm not going to show you the tour through E8 today. You can do it in your free time afterwards because we're running out of time. But I'll just sum up. Well, we've seen Magma, which is a powerful tool for computational algebra and number theory, and how you can do things with lattices and quadratic forms in Magma. We've seen a little bit about quadratic forms and the Hassan-Minkowski principle, and I'm sure Keith will tell you a lot more about quadratic forms during this week and local global principles. And for lattices over the integers, this principle fails, and things that interest us a lot about these things are exactly quantifying the failure. So these are the class sets, and we can use tools like Magma and the LMFDB to compute them, to store them in a database, look them up, and understand them better. So tomorrow we'll talk about number fields and relate things to the Kronecker-Weber theorem that Laurie was talking about.